This ordinary difference equation is a classic example for the existence and uniqueness theorems. And so it's not that terrible of an equation, but let's dive into it. So we have y prime equals 2 times the square root of y. So it doesn't look terrible. And we're given, we have to apply existence and uniqueness theorem to this, y prime equals f of x comma y, and initial condition y at x of x naught equals y naught. So the first thing to do is identify f. So we have f of x comma y is equal to 2 times the square root of y. There is no x dependence. So now the question there is, when are we going to have problems? So, only makes sense for y is greater than or equal to 0. And so the reason we can't have negative numbers is, we can't take the square root of a negative number. That's going to end up with negative, imaginary slopes. Who knows what that means? But we can have it equal to 0. The square root of 0 is 0, so that's okay. And we can also have it greater than 0. The square root of a positive number is going to give out a positive number. All right, so that's looking fine. Then we have partial f, partial y, and they go through the steps again, right? That's partial y applied to the f function. The f function here is 2 times the square root of y. To make that a little easier, I'm going to write it as partial y times of 2 times y to the 1/2 power. All right, so now this is a power rule. We're going to take the derivative of this whole thing with respect to y, treating x as a constant. There are no x's, so we don't have to worry about that. So we're going to have our 2 stick around, that's a constant. Taking the derivative of y, we're going to have a power rule pop down a 1/2. Then y will decrement its power, so that'll be y to the 1/2 minus 1, so that's negative 1/2. And there is no y prime that pops out. So the partial derivative won't pop out of y prime. We treated y as the variable. It's not a function of x. All right, and another way to write this, so the 2 and the 1/2 cancel. Y to the negative 1/2, that's 1 over the square root of y. All right, so this only makes sense when, this one's slightly different, y is, let me draw a better y there, y is greater than 0. Right, so 1 over the square root of a positive number, that's going to be okay. But if y is equal to 0, we get 1 divided by 0, that's not okay. And we can have, if y is negative, again, we have the square root of a negative number, that's an imaginary number, that's not okay. So this really only makes sense when y is greater than 0. All right, so now for existence and uniqueness, we're going to have some interesting stuff here. So let's draw out some points. So if I have this axis is x, this axis is y, if my initial condition is up here, then I can draw an open rectangle around that. And inside the open rectangle, f and partial f partial y are continuous. All right, well, okay, right, so that makes sense. So existence and uniqueness theorem then, if f is continuous in the open rectangle around the initial condition, x naught, y naught, then we're guaranteed at least one solution around this point. But I also have partial f partial y is continuous in this open rectangle around x naught, y naught, the initial condition. I also know I'll have a unique solution going through this point. And right, I could expand this box to be bigger, but this is good enough right now. Well, okay, what if we do it a little differently? What if we have the point, let's say it's right here, x naught, and then y naught equals 0. Right, it's right on the x-axis. Now I've got a little problem. I can't actually draw an open rectangle that contains that point, that is continuous for either f or partial y. The reason for that is if I put the rectangle right on the axis, it won't contain the point. This dashed line means it doesn't contain its boundary. So we actually don't know pretty much anything about what happens for the solution when it starts on the x-axis. We know for sure we have an existing and unique solution if the initial condition is a positive number above the x-axis, but we actually don't know anything if it's on the x-axis. And then to start lower, so we have x, we have y. If we put a point down here, that doesn't really make sense at all because we can't put a negative number into the square root. We'll end up with an imaginary slope. So this one doesn't, work at all. So let's go ahead and investigate. So, we should have an existing and unique solution here. And let's go ahead and solve this and see what happens and how the existence and uniqueness theorems play into this stuff. And so this is a separable equation, so let's go ahead and solve it. So this is dy over dx is equal to 2, and I'm going to write square root of y as y to the 1/2. All right, if we go ahead and separate that, we'll end up with, dividing by y to the 1/2, we end up with y to the negative 1/2. dy on one side, then multiplying by dx, we get 2 dx. Then we can integrate both sides. All right, so that's going to end up turning into, so y to the negative 1/2, that'll reverse power rule, that becomes y to the positive 1/2, adding 1. But then I have to cancel out that 1/2, so when I take the power rule, so I'll put a 2 in front here. And on the other side, I have 2 dx, that'll turn into 2x, and then plus the constant of integration. Now, if we solve for y, we'll get, first I'm going to divide by 2, so I get square root of y equals 2x over 2 is just x plus c over 2, but a constant over 2 is still a constant, so let's just call that x plus a constant. And then if I square both sides, then we end up with just y equals x plus c squared. But there was something to watch out for right there. So y can't actually be, the square root causes some problems. So you can see that. So if I draw these out, you would think that if I have some solution, xy, it's a parabola and it has a double root when x is equal to negative c. So it's going to be these parabolas that are going to touch the x-axis. And I'll draw another one over here. There's a whole lot of them. And those are all the solutions. But there's a little bit of a problem. On this half of the parabola, we have a negative slope. And then on the right side of the parabola, the right half, we have a positive slope. And for all these parabolas, the y value is always greater than or equal to 0. So that gives us a little problem. So if we actually go back to the original differential equation, if we plug in a value for y on these parabolas, y is always positive, the square root of a positive number is going to be positive, y prime is always going to be positive. And that's a problem because on the left half of the parabola, the slope is negative. So this left half of the parabola actually doesn't work for our ordinary differential equation because we can't plug in a positive value for y, and so 2 times the square root of y is going to equal a negative slope. It just won't happen. So it's actually this half of the parabola isn't a valid solution. Okay, well that's kind of weird. Well, what happens then when the parabola gets down to the x-axis? Well, it turns out there's another solution here. So the other solution is y of x is equal to 0 all the time. It's just the x-axis. And so if you do that, that does end up working. So our equation was y prime is equal to 2 square root of y. If we plug in 0, we get 0 prime equals 2 times the square root of 0. And yeah, that is true. 0 does equal 0. This is a solution to the ordinary differential equation. And so the solutions actually end up looking like this. So we've got x, we've got y. If we have an initial condition up here, we were guaranteed an existing and a unique solution, and it turns out to be half of the parabola. It's going to be a little hard for me to, okay, I kind of did it. Pretend that's parabola. So it's going to be the positive half of the parabola, y is equal to x plus c squared, where this point here is picked by the c. And then after that, it's going to be a flat line going along the x-axis, going backwards. And so if we have a point up here, we're going to have an existing and unique solution. And even when we got down to the x-axis, when there were potential problems, it's still a unique solution for this initial value problem. But the opposite isn't true. And I'm going to have to squeeze this in. So over here, at x, we've got y. What happens if I start on the x-axis? Well, okay, so I can't have the negative parabola. And let me just write, I can't have this half the parabola. That part doesn't satisfy the original ordinary differential equation. So if I start here, I can't go up on the backwards parabola, the left half, but I know I can go backwards forever. So that's the solution. And I can also, jump up to the parabola. But I don't have to. I could also start at this point, I could stay flat for a little while, and then I could jump up to a parabola. Or I could go a little further. Oh, come on. Or I could go a little further, and I could jump up to a parabola. So points starting on the x-axis, when y naught equals 0, have an infinite number of solutions. You have one solution if you go backwards in x, but if you go forwards in x, you can jump up to the parabola immediately, this other solution we have, y equals x plus c squared, or you can wait a while and jump up to a parabola, or you can wait a lot longer and jump up to a parabola, or you can choose to never jump up at all and stay just at x equals 0 forever. So starting at a point that's above the x-axis when y is positive, y naught is positive, you have a unique solution and it exists. But if you start on the x-axis, you actually have an infinite number of solutions you could choose from. And so this is kind of illustrating the limitations and also the power of the existence and uniqueness theorems. So the limitation was we didn't really know anything about starting on the x-axis from the existence and uniqueness theorems. And this is also why this is a very classical example for existence and uniqueness theorems. Even though it's a very simple looking ordinary differential equation, it's y prime equals 2 times the square root of y. It has this very, very interesting behavior. So we're going to see some more interesting behavior in some of the other examples.